Now let us do application. In order to confirm ourselves, let us look at the scattering dielectric sphere, epsilon and epsilon 0 outside. And the variation in the dielectric constant is delta epsilon, epsilon minus epsilon 0. Again, R is the radius. So there is no any variation in the magnetic permeability, therefore this term is 0. You have delta mu is equal to 0 and delta epsilon is not equal to 0. So basically this part is 0 and this is there, and what is k and 0 minus n we called as a q, change in the wave number before the scattering and after the scattering. So if you want to calculate this for this problem, result will be the following. K to the 4, no, k square, I'm sorry, square will be the k to the 4. You have polarization before the scattering, dot product polarization after the scattering. Take the outside integral. You have the constant variation. Variation in the dielectric constant is constant. So it is something like this. Epsilon as a function of r is something like this. Okay. So this is r equal to a, not 0, it goes to epsilon 0. From epsilon to epsilon 0 it drops. Therefore you can take outside the integral, delta epsilon over epsilon 0, and polarization after the scattering, dot product polarization before the scattering. So in your book, dielectric constant of the vacuum is epsilon 0, and epsilon 0 hat is a vector, unit vector, and that represents the polarization. Okay. And then you have an integral of d cube x primes. So let's say that this is the z-axis, and this is some theta from the z, theta, angle from z. So your integral will be what? R square sine theta d theta d phi. This is the volume element. You can say in terms of primes or unprimes. And e to the I q. What is q dot x prime? Q dot x prime is nothing but q r cosine theta. Integral have to be taken. For dr integral have to be taken 0 to a, and theta and phi integrals have to be also taken. So theta and phi. Phi goes 0 to 2 pi, theta goes from where to where? 0 to pi. So I am not going to take this integral. So if you take the integral, obviously r goes to the a, so you have some qa terms and angular terms. So for radial term, you can use the by parts, integration by parts. You can lower degree 2 times by parts. That will lower the integral degree. Then you will get the following result. So integral is trivial. You can easily handle this. Variation of epsilon over epsilon 0. Polarization after the scattering, dot product polarization before the scattering. And the integral will be the following. 4 pi sine qa cosine QA over Q cube multiply A cube divided by A cube, and so this is in terms of Q times A, because our integral goes to the surface of the sphere. So in the long wavelength limit, we are working in the long wavelength limit, QA is nothing but QA as a magnitude is nothing but, what is the QA? Q K 2 pi over lambda is the order times A. This is the order, okay, or 1 over A is the order. In the long wavelength limit, lambda is much greater than A, okay. So QA is a magnitude, order of magnitude of QA is nothing but the size of the scatter divided by the wavelength. This is the order. Let's say order. Basically, in the long wave limit, QA goes to 0. In the long wave limit or long wavelength limit. So this part, when QA goes to 0, using the Hopital rule 2 times, is nothing but 1 over 3. So I am trying to concentrate with the results, so I am leaving the integral and the Hopital rule application to you. So basic thing, we have the variation in the dielectric, variation in the dielectric constant due to the one single sphere. And the second thing, when you take the integral, you can go to the long wave limit taking the QA as a 0, because Q is a proportional to inverse wavelength and A is the size of the scatter. A over lambda have to be have to go to the 0, has to go to the 0. Then the result will be the following. So this is 1 over 3, and you have A cube. Then if you write the full definition of the scattering cross section per salt angle, you have to take the square of this. So K to the 4, so 4 pi's will be cancelled, and A to the 6 we have K to the 4, A to the 6. Variation in the dielectric constant over epsilon 0 square times 1 over 3 square times polarization after the scattering, dot product with the polarization before the scattering, square, I think, yes. Anyway, that will be the result. Just take the square of this. Take the integral, apply the Hopital rule, and write the result. Is this result is consistent what we have done in the past? If you go to the radiation approximation as a scattering, we trade it, we work on. So we find that the scattering cross section per salt angle is K to the 4, A to the 6, E over epsilon 0 minus 1, epsilon over epsilon 0 plus 2 square epsilon complex conjugate dot epsilon 0 square. So we derive this, we write this as a epsilon, and epsilon was nothing but the ratio of the epsilon to the epsilon 0. Are these two formulas the same? So coefficient is the same, k to the 4, a to the 6 is the same. So the polarization terms is the same. There seems to be some difference here, but let us look at that. It is a difference, or indeed they are the same thing. So if you look at this term, that is nothing but epsilon minus epsilon 0. That term is nothing but epsilon plus 2 epsilon 0 square. Epsilon minus epsilon 0 is nothing but variation in the epsilon. The below term is the following. So add with epsilon 0, subtract with epsilon 0. So if you look at here, that is nothing but 3 epsilon 0 plus variation. 3 epsilon 0 plus variation, but we know that the variation is small, so this is not important. Therefore, this is nothing but 3 times epsilon 0 square. So they are identical. So this is working well for a single scatter with radius a. And actually, this is valid not only long wavelength scattering or for any wavelength, because we are not doing any kind of radiation dipole approximation. We are using the general theory of we are using the Maxwellian theory. We write that the non-homogeneous wave equation and solve. Now let us come to the explanation of the blue sky. So suppose that in the medium, in the air, there are dipoles, electric dipoles, at any point. And electric dipoles is related with the external electric field. And the proportion to the constant is related with the polarization. So gamma mole is called as a molecular polarization. So the electric field is the what? Electric field of the what? Electromagnetic waves. And that induce some polarization. And each molecule has the proportion to constant, which is the same for the air molecules, and you can write the electric dipole moments in terms of the external electric field, and electric field is the oscillating fields. What we have to calculate? We have to calculate the cross-section per solid angle, then we have to integrate this. So if you look at here, you can easily see that the variation in the dielectric constant is nothing but the proportion to constant between the electric dipole moment and the electric field, and that is epsilon 0 times gamma mole, and they will be distributed in the space in the atmosphere randomly, x minus xj, and j is, let's say, 1 to n. So the relation between the electric dipole moment and the external electric field is nothing but the variation in the dielectric constant. So if you want to calculate that the scattering cross section per solid angle, we have to again calculate this above term, but again there is no variation in the magnetic permeability, and we can write this term in the following form: epsilon complex conjugate that is scattering amplitude over d0 is equal to k square over 4 pi d cube x prime, or yes, d cube x prime e to the I q dot x prime, the above term. Then polarization before the after the scattering dot before the scattering. And what else? Variation in the dielectric constant over epsilon 0, that is nothing but summation of j1 to n gamma x minus x prime j, x minus x prime j. So if we take the integral, what we are going to obtain? Instead of, so let us say not the x minus x prime, x prime minus x. So if you take the integral for x prime, you will substitute xj, and your result will be the following. Take the summation outside the integral, because this is finite. Take the through the integral d cube x prime. So we have, delta functions here. Delta function x prime minus xj. So basically we distribute this dipoles is a single delta functions at discrete points. So at each discrete point you have some distributions of the electric dipoles. So distribution of the electric dipoles are represented in terms of delta functions. So if you take this integral, you will end up take this summation outside and take the integral. The result will be k square over 4 pi epsilon complex conjugate at epsilon 0 gamma summation through the j1 to n e to the I q dot xj. Instead of x prime, you will substitute xj. Again, you are seeing that if you take the square of this, you have to take the square of this, and this is again a structure factor. And this structure factor for totally non-uniform distributions is nothing but the number of scatters. If you have a crystal or lattice, you have to know that structure factor. But for that case, that will be the just number of total scatters. So basically, when you calculate that the scattering cross section per solid angle, you have to take the square of this. That will be equal to square of this term, and that is nothing but k to the 4 16 pi square gamma square polarization after the scattering, that incident polarization, and this term e to the I q xj square, and this is nothing but the structure factor, and that is the for totally random scatters, that is nothing but that is equal to number of scatters for one molecule, that will be 1. So I'll take this term as a ratio here, that will be the scattering cross section per solid angle per one molecule. So let us move on to calculate the gamma. So we are coming to the end quickly. So the next thing is the following. So the dielectric constant, relative dielectric constant relative to the vacuum, epsilon over epsilon 0, is roughly 1 plus number of molecules times the gamma. So from here the gamma is the dielectric constant of the air minus 1 over number of molecules per volume. So take this and put it there. So we will get the following. The scattering cross section per solid angle will be k to the 4 divided by 16 pi square. Instead of gamma square, write the square of this over n square, and polarization after the scattering, dot product polarization before the scattering, and you have the structure factor. And let us do a simple thing here. So this is equal to in terms of refractive index, the square of n square minus 1. This is n is the refractive index. You know that the refractive index is related with the square root of epsilon, and mu is the same. So the refractive index is nothing but square root of epsilon over epsilon 0. So remember that that is the definition. N is equal to mu epsilon over mu 0 epsilon 0. So mu 0 and mu is the same. So that is nothing but the square root of ER. ER is the ratio of the dielectric constant relative to the vacuum. And this is nothing but n minus 1 n plus 1 square. For air, this n is close to 1, and that is nothing but 2. That is nothing but 4. The addition is close to 2, and that will be 4 times n minus 1 square. So, and what is the other term? The polarization stuff. So if you remember that what we have done for the polarization scattering from the dielectric sphere, we take the unpolarized incoming wave and we studied that the polarization after the scattering, and we find the formula. We find the formula in that form: 1 over 2 1 plus cosine square theta. then if you integrate this scattering cross section per salt angle through the all salt angles, you can find that the total scattering cross section. So for the salt angle integration, you need to calculate this, and I write this result from the without integrating. You can integrate this. That should be, I think, 8 pi over 3. So the overall result will be the following: k to the 4 16 pi square, and from here you have 4 n minus 1. N is the refractive index of the atmosphere, divided by n square. N square is the square of the number of molecules per volume, per unit volume. So integration of all stuff through those salt angles will be 8 pi over 3. You can derive this by yourself easily, times the structure factor. This is the number of molecules, and so anyway, this have to be the following: the scattering cross section per salt angle approximately will be 2 over 3. Is this right? Is it 2 over 3? This is 1 over 2. Yes, that's right. So coefficient is not very important. K to the 4th and times pi square, number of molecules per volume square, n minus 1 square times the structure factor. So for one molecule, this is nothing but that. So n is close to the 1, but not exactly. Difference is important, but the addition doesn't very much important. Addition is roughly 2. N plus n1 is roughly 2. So this is the scattering cross section for Rayleigh scattering, and here we are seeing that again the scattering is increased at high frequencies. So for Rayleigh scattering, 2 over 3 k to the 4 is what? Omega to the 4 c to the 4 over pi square n square n minus 1 square. So basically, scattering is cross section increases at high frequencies. And another thing, that is the absorption coefficient, important thing. So when if this is the Earth, we have the cases: sun is rise, set, and top. So that should be sunset or rise. So during the sunrise and sunset, atmosphere is more thick. There are more scatterings. When sun at the zenith, atmosphere is thin, less scatters. So basically you can define that the absorption coefficient also. So if there is a incident radiation, that drops exponentially. So x could be this one, x could be here or here, it doesn't matter. If there's an incident radiation, due to the scattering, we can see that the light is absorbed. Okay? So if you use that radiative transfer equation and solve this, you will find the exponential. This is very standard. The absorption coefficient absorption coefficient, if you look at the scale, if this is a distance, there should be what? Exponential 1 over length. So this should be unitless. Okay, alpha times x should be unitless. So how you can define that the absorption coefficient if you know that the scattering cross section? What was the unit of the scattering cross section? Area. Therefore, if you multiply this some quantity, you can get that the absorption coefficient. And what is that quantity? Scattering cross section is the same, but medium is different. So basically, you have to know that the what? You have to know that the number of molecules per volume. Okay? We know that the number of molecules per volume. If we multiply with the scattering cross section with number of molecules per volume, we can obtain that the absorption coefficient. Okay? So even the scattering cross section is the same. If the medium is changed, the absorption coefficient will be different, and the radiation will decay as exponentially differently. Okay? So if you look at that, what is going on sky, the situation is the following. Absorption coefficient is more or less same during the sunset or sun at the zenith, more or less the same. But the total distance at which the beam travels is different, because during the sunrise and sunrise the atmosphere is thick, and at the zenith when the sun is up, atmosphere is more thin. So absorption is less when the sun at the zenith. So if you look at what is going on in terms of the numbers, is the following. Let us look at the three colors: color red, green, violet. So this is 6,500 Armstrong. This is 5,200 Armstrong, and this is 4,100 Armstrong. So it is sun is zenith, and during the sunrise or sunset, the situation is the following. At the zenith, 96% of the red passes to the Earth observer. 90% of the green passes, and 0.76 is passes. Okay, so yes, higher frequencies scattered more, but the order of magnitudes are similar. Why? Because of the absorption coefficient is the same, but the total distance is not much. But during the sunrise and sunset, atmosphere becomes thick. So total distance at which the light beam travels increases. And the situation is the following. The 20% of the red reaches to us. 2% of the green reaches to us, and only what is this? 1 in 1,000, 6 in 1,000 reaches to us. Okay, lots of scattering of the high frequency waves during the sunrise and sunset. The mixture of the combination, I think, this should be blue, and the mixture of this is definitely red. Okay, so that is the Rayleigh scattering, and as I said earlier, first this is considered by Leonardo da Vinci in 1500th century. He thinks that atmosphere is white, sun emits white light, but at night it is dark. He tries to combine the white and little dark and tries to make a blue color. And 370 years after him, by what was the Rayleigh, that is an English scientist, proposed that the scattering of the sky is blue because there are scatterings from the electromagnetic waves from the molecules. One good example is the following. You know that you see that, I think, lasers at night in holiday resorts and so on. They use it which color? Do you remember? Do you remember that the holiday resorts, the laser beams on the atmosphere, they make some shows, laser shows? No, don't say red. So that is, they are using green. While this is also okay, because you can see the whole beam at night of the green, because they make lots of scatterings and we can see that light. Okay, that is the reason they don't use the red. Now we come to the last section of this chapter. We will start on Monday, that is diffraction. And I think next week, today, we will be able to start the relativity. Okay, we have only 2 hours, I think, for spending time for diffraction, and that will cover the whole chapter.